Okay, there are still 3 minutes to go. Maybe I can use the time to announce that on the in the week of the 18th September, that's a Wednesday, there will be no, due to a holiday, there will be no lecture on Tuesday. And instead there was announced a lecture for Friday, but this has been shifted to Wednesday. And it will be start an hour earlier at 13:20. No. Yes. Was it 50? Anyhow, it's and it will be in a different room in AH31. But the information is on the website, or will be on the website. But what I want to add to that is that this will officially end at 5 minutes past 4, but I already have another commitment at 4 o'clock, and therefore I plan to reduce the breaks from 10 to 5 minutes. So just that you already know that. Okay, let's continue. Last time we gave the definition of additive and abelian categories and various notions that we have for those types of categories. And the last one was more or less the one of kernel and co-kernel. And now there will be another definition for morphisms, which we will also use quite often. And we say that the image denoted by im of f of a morphism f, say from x to y in a category C. This is a pair consisting of an object I in C and the morphism which I call G, which goes from I to Y, such that the following holds. First of all, G is a monomorphism. And then F, the morphism we start with, can be written as G composed with H for some morphism H, which by definition here will be from X to I. And in addition, this property is universal. So if there are any other pair, I prime and G prime, such that we have F equals G prime composed with some H prime for some H prime from X to I prime. and also that this is a monomorphism, then there exists a unique morphism. We call it T from I to I prime, such that G and G prime are related by composition with T. And analogously, one defines the co-image. Co-im of F by just reversing all arrows, or in short, one can say that this is the image of F for F regarded as a morphism, not in C, but in the opposite category. Then remark. First of all, this generalizes the conventional definition of image of a function. So if we have a function f from x to y, then I is nothing but f of x, and g is the embedding of f of x into y, and also h is just essentially f, but f regarded as a function or map from x to f of x. Then, because of this universality property, as usual, in general, the image of a morphism will not exist, but if it exists, then it's unique. Or precisely unique, unique up to a unique isomorphism. And also, the H that we introduce here, and given a G prime a T, are also unique. So because of this this uniqueness here, we call this the image. In principle, if you take the definition very seriously, we'll have to say an image in the beginning, because we do not yet know that is essentially what we want. Another comment: assume if C has all equalizers. Equalizers are a special type of limits. Then it follows that H, the morphism in this factorization, F equals G times H, is an epimorphism. And in case C is abelian, which is the situation we are now particularly interested in, then it follows, in fact, that images and co-images always exist, and moreover, every morphism F from X to Y factorizes in the following form. We have an epimorphism from X to the image of F, and then we have a monomorphism from the image of F to Y. This is one concept we will use. Another concept
sorry,
oh.
F itself is a monomorphism, then the image is XF. If F is already a monomorphism.
If F is already a monomorphism,
then we can take G for Fx.
then yes, yeah. Then we can take I to be X and G to be X. So the second is the notion of direct sum. And we first have to tell in what situation this is defined. We take C to be a category with all products. All products exist. All co-products. Don't write all again. Co-products and with zero morphisms and images. So all images, every morphism has an image. So, for example, C is abelian, but this is more general. And then we say that xi for I in some set capital I, not to be confused with the I here, so we use the same letter, be a family of objects in C, indexed by a set I and let Ri be the morphism from the co-product over I xi to the product over I xi. Both of these exist by assumption. That is defined by having components. Let me see, this is not, it should be R. With components of the form, if I start with, if I take xi embedded into the co-product, then apply R to go to the product, and then project to some xj, then this is either the identity of xi if I and j are equal, or it's 0. But to be precise, the 0 morphism from xi to xj. And then we say the direct sum over these objects That's this direct sum symbol, I over I xi, is the image of the following morphism. No, the image that we obtain as taking the co-product, then forming via the co-image of R, we come to the direct sum, and via the image of R, we go to the product. Why did I write is the image? Because well, via the image of R, we can see this as a sub-object of this. And now, from this definition, we know that in general, the direct sum is somewhere in between the co-product, which is larger, and the product in general, and the product which is smaller. But of course, if C is additive, I have mentioned last week that finite products are finite, same as finite co-products. It was in 199. And that means that finite direct sum is also the same as those. And another example, let's take C to be the categorical groups. For this, we have mentioned that the product is the Cartesian product and the co-product is the free product. So they are not equal, and then this means that the direct sum is in between them. I should write it in this order. Product. Cartesian product. And a definition that we also will use, and which doesn't fit very nicely anywhere, I bring here because it's again about direct sum, but now about direct sum categories. There are two categories called them A and B, same symbol of two, and we assume that they are additive. This is by definition a category with objects. An object is a pair, let's say XY. I took XY. But then where X is an A and Y is an B. And then the morphisms in A plus B between a pair XY and a pair X prime Y prime is just the direct sum of vector spaces. X prime. of the morphisms in A between X and X prime, and those in V between Y and Y prime. Sorry, not of vector spaces. I should have corrected me. We are here in the context of additive categories. So these are abelian groups, and then we take the direct sum of abelian groups. I was confused because I will talk about vector spaces. There is a
question about group.
Yes.
If I understand, you said group category do not have zero. The notion of direction is not defined.
That's a good question. I have to check this out. I cannot answer this.
Because otherwise, what is the difference between direction? What would be the direction?
I will check it out. At the moment, I cannot answer it. Actually, when I wrote down this here, I realized that I'm not sure about this. I have to reconstruct where I took this from. So these were some further definitions, and now we will have more definitions, but this is now the whole area which is one reason why abelian categories are important, and this concerns the notion of exactness of a function. Here we need some preparation. Definition of various things, and we at the moment define it for the abelian case. One can be a bit more general. I will mention that afterwards. We say that chain complex, or more precisely, a Z-graded chain complex, which we denote by C with some index of block in C. This is by definition a collection of objects Ci or Cn. N is an integer, and a collection of maps, morphisms, which I call dj or del j, such which we then write in the following way. We have say C2 somewhere and C1, then we call this here D2. And then from C1 to C0 we go by D1 and so on. And also in this direction. And we require that if we go 2 steps, then we just get 0. So dj after dj plus 1 is equal to 0 for all integers. And then we say that the chain complex is exact at some position, say Cj minus 1, if and only if we have that the image of dj equals the kernel of dj minus 1. Then we say that an exact sequence in C is a chain complex in C, which is exact at every position. So at every, say, at every. I call, and I'm talking about exact sequences. I use the notation X. At every X, X n. Definition is still not finished. We say that we deal with a short exact sequence. And see if we have such a sequence which is short in the sense that we have three general objects which I call S, X, and Q, and all the other objects are 0. And then I call these morphisms here I and R. And usually, since there is no information contained in the rest here, we just leave this out. So we call this here a short exact sequence. And once we have this notion, we can now define what an exact functor is. The f from C to D this is an functor from C to D that preserves exact short exact sequences. So if we have a short exact sequence, 0, S, X, Q, 0, then if we apply the functor to it, well, if we apply to 0, we get 0 again, and then we get a sequence like that with f of I and f of R. These places, then this should again be an exact short exact sequence. And this should be true for all short exact sequences. Exact. And then we also define the left exact sequence functor. There is one which does not necessarily preserve all short exact sequences, but those where we do not require this part. So and analogously, then of course the right exact functor is one which preserves exact sequences of the form where we leave out the 0 on the right. And the reason for introducing this concept is, first of all, that we can make statements about such functors which are of interest, and then there are interesting functors which have these properties. And the first of these is we assume that C is abelian, and then we have that the Hom functor is a functor in the second argument. So Hom x, which goes from C to C, C to well, in general set, but it's abelian, so it's in particular an abelian group. Is left exact for every x in C. And similarly, I don't write this down. If you take the Hom functor, maybe I should write explicitly C here. The Hom functor, an arbitrary object to x, which is then a function from C opposite to abelian. This will be right exact. And as a functor from C up, but if we can simply say it's left exact as a functor when we and I don't want to prove this. Maybe if you should try to convince yourself, I think it's one of those things which are kind of obvious, so that it's easy, not so easy to find a formal proof in the literature. But the idea is simply that essentially automatically the Hom functor preserves limits, and then you use the definition of limit to see that it is left exact. A refinement of this sorry, not a refinement, a definition. Again, C is abelian. We say that an object P is called projective if and only if the Hom functor with P, or an arbitrary x, is not only left exact but also right exact, so it's exact. And we say that an object is injective if and only if the contravariant Hom functor is exact. And there's a good chance that many of you have seen definition of projective and injective objects which are not this definition. And then maybe it's a good idea to check that there. It's just a rephrase. Now these properties are important, but they assume that C is abelian. However, it's actually not an extremely strong restriction to consider abelian categories. And this is because of the following important result. Proposition. This is called the Wright-Mitchell embedding theorem. It says that what I said was not the right way to present things. Every abelian category is a full subcategory of the category R mod, so modules over R for some ring R. And not only that, it's in such a way that the embedding functor is just a functor which sends every object in the subcategory to the same object in the category and unlocks the homomorphism that it's exact. And what I said before formulating this was not quite sensible. Change the formulation here. So the theorem is important because it allows one to get to obtain results for abelian categories by looking at results for R mod and which in some cases might be easier, and then restrict to conclude something for subcategories. And here I give a reference right, which is freely available as a volume of theory and application of categories, and it's chapter 4.4. And I still not produce a list of references, but I started and we will get it soon. As an example on how you can make use of this theorem, let me mention that so the following lemma: the sequence is exact, well, a short sequence. If and only if we have the following: I is a monomorphism. R is an epimorphism. And image of I equals the kernel of R. Well, this is actually this is obvious because it's part of the definition of exact sequence, and so one really only has to prove the first two statements. The idea here is that we first consider that C is R mod. and in that case, and that's the advantage of having such a concrete realization is that we can work with elements. And then invoke the fried Mitchell theorem. Of course, you need many more details, but this is the way or the reason why the theorem is important. If you have a category R mod, R is a ring, so it has elements, and you can make statements about elements. We need a break soon, but let me start anyhow with next part. This is more side remark. It's not hard to generalize the definition of exact sequences or functors then to additive instead of abelian categories. But one can do it even a bit more generally. And let me just start with this. We consider category C and D that are finitely complete. And a functor from C to D. And then we say that F is left exact. If and only if it preserves finite limits. And it's clear in the abelian case, this follows from the definition there. And similarly, we say that, maybe we should do it like that. Let C and D be finitely co-complete. Then we say that F and F, again a functor from C to D. Then we say that F is right exact. If and only if, well, it preserves finite coordinates. And I don't write the third part, the time is over anyhow. If C and D are both finitely complete and finitely co-complete, then we can say F is exact if it preserves both finite limits and finite coordinates. And then that's have to go. I'm not sure, should we stop the recording and start a new one afterwards, or I can get this wrong? For me, it doesn't matter.
Just a little bit, yeah.
Okay. Okay. But when do we start then? Already also 5 minutes left. Okay. So we stopped 5 minutes too early because I was apparently confused about the time. So we will start in 3 minutes and then have 15 minutes until 4 o'clock. Until 3 o'clock. No, let me see, until 4 o'clock. Yes, and then 4:10 and 4:50. Okay, let's continue. So we are still in section 1.7, additive and defining categories, but we are almost finished. There are just two addenda here which are not directly relevant at the moment, but which we will take up later on. The first is a comment. There is an important connection between the notion of exactness of a functor and the notion of adjoint of functors. But we have not talked about adjoint functors yet. This will actually be one of the next subsections, and then this connection we will I think take up in the last subsection of section 1. And the second comment here is that there is a notion of opposite functor which we will use every now and then. And I don't give a formal definition here, or maybe essentially I give, but I don't call it a definition. So we call this F opposite for a given functor, and what is it? It's a functor from the opposite category C op to the opposite category D op for a functor F which goes from C to D. And this is not something new, but it's simply the same map on objects and on morphisms. Remember, the objects of the opposite category are just the objects of the category, and the morphisms are just the morphisms, except that we label them differently. And in order to make this a bit less trivial looking, it's nice to have the following notation, which I will use every now and then, but not always. Because very often it would make things unnecessarily clumsy, but sometimes it makes things more easier to grasp. Namely, we say that if we have an object X, then we write X bar for the same object, but regarded as an object in the opposite category. And then what this says here is then that if we take the opposite to a functor, we have to apply it to an object in the opposite category, so to X bar, where X is in C. Then this is the same as f of X, regarded as an object in the opposite category D bar. So we have a bar here. Well, it's not the same bar, it's the bar for D. And analogously, if we have apply this to a morphism, so a morphism in the opposite category. So if f goes from X to Y, then f bar will go from X bar to Y bar. And then this is just f of the original morphism, which goes from X to Y, regarded as a morphism in the morphism from here to here. So now we come to the next section, which I just call linearity. So we will now consider a class of categories where there is a linear structure in the sense of vector spaces over some field, which as before we call it K. So maybe first an observation. We have used K vector spaces as one type of categories. That's an interesting example. And if we look a bit closer at this, we see that the morphisms, which a priori are just sets, are in fact themselves vector spaces. If you look at the linear map between two vector spaces, it's again the vector space. And if you look at their composition, then it's linear in each of the morphisms, it's bilinear. And this is a feature which is shared by other categories, many important ones, and therefore we define a category with these properties. Let's call it C. With the morphism sets are to repeat this co-vector spaces and bilinear composition is called, and there are long and short names for them. One is enriched over the categories vector spaces. This is a long terminology, therefore one also just calls them K-linear, or in most cases the field K is fixed or obvious, then we just say linear. Then we talk about linear categories. And in this situation, we have the following terminology, which I may not use very often, but I might use it. So the field K is also called the ground field. You will see this terminology quite often. And there's another name for these categories, which I will never use, but I mention it because it's mentioned on the NCATLab website. It's sometimes called an algebra. But you have to be careful that this terminology can also be used for other things, possibly by other authors, so I will definitely not use it. Let's take a simple example, which is not vector spaces. Remember the category, which is just one object, and where the morphisms are given by an algebra A. This is a K algebra, then this is K linear. Clearly. And a remark concerning this terminology enriched. So this is just of a more general concept of being enriched over a K, where K is some category, but not an arbitrary category. It has to fulfill some requirements, and one is seen as follows. So enriched over K, or one also says K enriched, and this you define as follows. Take the definition of, to be precise, a locally small category. And replace morphism set by, you can call it hom object, where this is an object in the given category. And then we have a composition of morphisms, so composition of hom objects. This amounts to what is called tensor product. on the category K. So K is what is called a monoidal category, and what that precisely means, of course, most of you know anyhow, but we will deal with this detail in the section 2. Actually, it should not just have a tensor product, but at least be braided, but in the ordinary case, the symmetric monoidal. Again, we will define what that is. There are, of course, also then definitions of enriched functors and enriched natural transformations. In the case of linear categories, it's pretty clear what that is, so I will not give a formal definition. Whenever we deal with K linear categories, and I do not say something else, then if we talk about functors, we mean linear functors, and if we talk about natural transformations, we mean linear natural transformations. And here maybe as a reference, for the details, there's first of all NCATLab. This is almost for every concept that we talk, and then there's a book by Wheel, and you will find a book in the list that I plan to have ready on Thursday. But first version, plan to have ready. Then various notions and results for categories generalize or have a variant for, in principle, arbitrary enriched categories, and in particular linear categories. And one of them I want to mention is an enriched Yoneda lemma. To be precise, the weak form, there's also strong form, which I cannot present right now, and I'm not sure whether I will present it at all. So this is now in the general situation, given K enriched functor, which I have not defined, but you can, I think, imagine what it is. F from K enriched category, well, in the Yoneda lemma, this was a functor to Z, so here it will be a functor to K. And an object X in C, then the set of K enriched natural transformations between the functors. It's denoted by alpha, as we did it in the ordinary lemma. So a natural transformation from the home functor of C to F is in bijection, in natural bijection, with the set of in quotation marks elements of f of x. If K is set, so if you have an ordinary category, not only enriched or set, if you like, then it's we really talk here about elements of a set, but in the general case, these are just the following. We consider the endomorphisms of X in C and go with alpha of x to f of x, and then because this category has to be monoidal, has a particular object in it, which is called the unit object, and there is a morphism from this to the endomorphisms here. Well, there can be, and the set of these morphisms is well, the collection of these morphisms are called, what these morphisms are called elements. But as I said, normally we will. There's one other example which eventually we will encounter, and instead of vector spaces, we might also use supervector spaces. But that will not be in the next few lectures. Another example. Which motivates some terminology. Recall that if we have a functor R, from this category, where now the morphisms are some group G to vector spaces. And then this amounts to a k-linear representation of G. Of the group G, we talked about this, and analogously, what I already mentioned, if we have a K algebra, then if we have a morphism to vector spaces over the same field, then this amounts. Don't need a name for this. Amounts to an A module by the same argument. And because of this, there's the following terminology. We call a functor f from C to vector k, where C is I don't know how much you have to assume about C. But we call this a k-linear representation of the category C. When we have a category and talk about representations of it, we mean functors to vector spaces. And there is one interesting example of such a functor, or an interesting class, which I want to mention, even though we will not at the moment deal with it. D-dimensional topological field theory, or some people say topological quantum field theory. Is, I put this in quotation marks and explain afterwards why, representation of the cobordism category over d minus 1. So in other words, this is a functor, often denoted by the letter Z, from this category. Okay, vector spaces. And in application in physics, the field typically is the complex numbers, but most of the statements hold for arbitrary algebraically closed fields. This quotation mark is because this is maybe a first attempt to define what this is, but actually both this category and this category, they have additional structure, which we'll come to in section 2, and it is required that the functor is not any functor between them, but a functor which preserves those structures. And let me give an example of such functors in the case of this category, or two examples. So assume we have such a G representation. I'll give this again a name R with an index V, where V is the vector space to which the single object is mapped. And then we can regard, well, this is a functor from a category which we can take as the category I that we used in the definition of limit and co-limit. So we can think of this as a diagram, this functor as a diagram, and then we can talk about the limit and co-limit of the diagram. And the result is that the limit of this functor turns out to be what is often denoted by V upper G. These are the invariants. So what is this? This is this set of vectors in the vector space V, which such that the action, which I denote by a dot here on V, is trivial for all group elements. This one calls the invariance. This, or in more detail, the subspace of fixed points of the group action. And another way to say this is, maybe I write this, it's the largest trivial sub-representation of the representation RV. In the co-limit of RV are what is called the co-invariants. Invariants are subspace, the co-invariants are quotient space, namely the space V divided by what is generated by the relation G in V minus V equals 0 for all group elements and all vectors. So this is the largest quotient with trivial G action. if G is finite, so that the representation category is semi-simple, which is a notion we have not yet defined, but soon will, then the two concepts are the same. And I conclude this section with two isolated concepts for which I didn't find a better place, but they are relevant in the context of linear or context of vector spaces. So they fit here, but we do not really do anything with them now. The first is very short. You can put it here. Definition, and it's a terminology which I like, but which is not very common. A linearly simple object. This is often also called an absolutely simple object, but there's no good reason for this terminology. And there are also authors which call this a scalar object. This is an object X in a category C such that the endomorphisms are in a linear category such that endomorphisms are just given by the ground field or isomorphic to the ground field, so K times the identity morphism. And various statements can be made about such objects which make them interesting, but mainly in the context or in connection with what is called a simple object, which is another concept that we will introduce very soon. And next is a concept that we will take up in several stages later on. This is the notion of pro-functor. From C to D, where these are linear categories. This is by definition a functor from, let me see what my convention is. Give it a name, H, from C up across the two vector spaces. And I should mention here that other authors and even the majority, I think, would not define it this way, but with C and D up. But that's just a matter of convention. In the linear case, of course, in the if we do not assume linear, then we can define the same thing here with sets. Or you have analogously enriched versions for other categories and vector spaces. And concerning terminology, if you look in the literature, it's important to know that instead of pro-functor, I think this is used rather often in the more recent literature, but in older literature, this is called distributor. In particular, in the French literature, distributeur, by Bosseux, for example, in his book. I should add the book to the list. These are 3 volumes, and they are very nice, but some of the terminology is maybe not the one that is mainly used today. And then it's also called module, which can be very confusing, at least to me. And this is mainly in the papers from Macquarie University in Sydney, and people related to them. So Ross Street and others are using this terminology. Notation. Instead of writing this out, one says that H is a profunctor from C to D, and one denotes it by this symbol here. So a little stroke here, and the stroke should be vertical. In some literature, you have a certain angle here because they do not know the LaTeX symbol for that. And remark is as a kind of action of a profunctor on morphisms both in C and D, say on F in C, then this has to go from X to X prime, so X and X prime in C, all morphisms in D from Y to Y prime. And schematically, this looks as follows. Take F, then you kind of compose this with H, not X, not Y, X prime, to get to Y. H goes from X prime to Y, respectively. We go from X prime with H to Y, and then compose this with G. Schematically, because these are morphisms in C or D, and these is something else, so there is a priori no way to compose them, but actually you can make sense of that by regarding both ordinary morphisms and profunctors as two different types of morphisms. You can get the concept of what is called a double category, and I hope that later in the course I can explain that.
So it's like a bimodule.
In some sense, yes. And as a final comment here, it should be kind of clear, but you can make this precise, that this subsumes and generalizes the notion of functor, namely whenever you have a functor, you get a profunctor, actually two of them. So assume a functor f from C to B, then you have a profunctor one from C to D and one from D to C, which are given as follows. What does a profunctor do? Well, it has to take an object in C op and one in D. And I don't use the bar notation now. I just write x and y, and it sends it. Well, it has to go to some vector space. We deal with linear categories. So it will be a space of morphisms, and it will be the space of morphisms in D from f of x to y. And the other one is maybe I should have called this x and y and then do the other one here. Oh no, it makes sense to do it like that. And you can check that these are profunctors. You just have to show that they are functorial in the sense that they send identities to identities and composites to composites. And you call these profunctors, you call them representable profunctors. Well, more generally, if you can describe, or not more generally, analogously, when you have a functor which such that you can describe it in terms of a home functor. And for example, the identity profunctor, where D is equal to C, is representable. You can check it just represented by the ordinary home, by the general home functor. This finishes section 1.8. Now we come to 1.9, which is about finite categories. So maybe for the general idea of these sections, we will, in applications, deal with special class categories, and they will have certain properties. And one of them will be abelianness, another one will be linearity, and another one will be simple type of finiteness. And sometimes you have all of them together, but sometimes you only have some of them. Actually, abelian will be assumed, or we will look at many k-linear categories which are also abelian, and at many finite categories which are also abelian. So 1.9 finite categories. And we start with a definition which is a bit more general than what we most of the time need. Namely, we say a locally finite category is by definition well, actually, when we finite, we will always assume abelian in k-linear. Technically, there are other notions of finite where one does not always assume that. But I will do this following the book by Ettinger et al. So this is a k-linear and abelian category, where in addition we have the following, and I have to apologize here for using a notion which I will introduce only a bit later. Every object has finite lengths. I don't want to say anything about it because I will define this in detail. And every morphism space, so each of the k vector spaces in C from X to Y is finite dimensional. The two aspects of finiteness, and the reason I accept here using something not yet defined is that we are more interested in a subclass of that, namely a finite category. This is a category, a linear abelian category that is equivalent as a category, but as a k-linear abelian category, so compatible with the structures to the category which I just denote by A mod of finite dimensional modules over a finite dimensional K algebra A. In situations where we would also look at infinite dimensional representations, one would here write explicitly finite dimensional, but this will not happen in these lectures. And now it turns out that every finite category is in particular locally finite. There is, in fact, a definition which does not use, which is not like that, which is very, very unconcrete, but which gives you a list of properties, including those locally finite. And then you show that it's equivalent to this description. But for our purposes, this will be perfectly fine. And here I note there's this book by Ettinghoff, Chelaki, Nikschitz, and Ostrich. And in this case, this is definition 181. And this here is definition, well, two definitions, 185 and 186. One of them is this, and the other one is the more explicit one. So we can put it up there. Just as a remark, we in examples 152, we have used the terminology essentially finite category, and there is no direct relationship between those. And one important aspect of finite categories is that there is what is called the linear product of finite. Some people call this also finite abelian categories. So there is a notion of finite where they do not require abelian, finite abelian, but we'll use this definition. And so of finite categories in this sense, kind of tensor products, which in a sense is a categorical analog of the tensor product of vector spaces, tensor product over the field. And to appreciate the definition, which I will give after the break, it's good to be aware of the fact, which maybe in elementary course is not so much pointed out, that the tensor products of vector spaces actually can be defined by a universal property, and should in principle be defined that way, because that's conceptually the most sensible way. But I formulate this as a lemma. The tensor product tensor over K of K vector spaces can be characterized by the following property, which is a universal property in the sense we have seen it before. V tensor over KW, where V and W are K vector spaces, is universal in relating bilinear maps from V cross W to, say, Z, where Z is any other vector space, to linear maps from the tensor products to Z. And you can make more words about this, but I will I refrain from this because I will make a few more words when I define the categorical analog of that after the break. Yeah, and I think it's a little bit right now. The break and we continue 4:10. No, it's 10. So as I said before, one important aspect of finite categories in the sense I define is that they allow for an analog of the tensor product over K, and this is called the linear product, or sometimes the linear tensor product of two finite categories. Well, actually, it's a bit more general. I should write this out. It works for finite categories, but even are two locally finite categories. Remember, this still assumes K-linear and linear. This is a K-linear category such that there is a functor which we denote by this symbol box times from the Cartesian product to what we call the linear product. That is right exact Well, in both variables, meaning if we keep an object here fixed, it's right exact as a functor from C to here, and this should be D. I mean D from D to here, or if we keep an object in D fixed, right exact as a functor of C to there. And is universal in respect this property. So for any k-linear abelian, I'm not sure, I haven't written that. Maybe one has to require abelian, but I should check this. But if I add this, it's certainly still correct. If you have any other k-linear abelian category, let's call it E, and functor, let's call it F, from C cross D to this E. Then there exists a unique functor converted by F bar from the linear product to this E, such that F bar, let's see, F bar composed with Ox time is given by F. Or maybe I should write it the other way around. So I can factorize the factor F into another functor and the derivative of that. And a unique functor and that is right exact in both variables. It's an universal identity property with respect to right exact functors.
It is universal among the right exact functors.
Yes.
So
let me see. Let me see. Did I? Let me see. It should be. I haven't written it. Let me see. I have to check this. The way I wrote it is that you do not require right exactness, but in the requirement of the unique functor, you require it. So you require that F bar is right exact, not necessarily F. Of course, if probably it's equivalent because it's equivalent. This is right exact, this is right exact, and a lemma that we could have formulated the composition of the right exact functions is again right exact. It's true. So there are various statements about the linear product, in particular between finite, not just locally finite categories that one can make. This is in Ettinghoff et al. Proposition 11.1.2. And probably the definition is probably 11.1.1, I guess. So various simple statements. First of all, if C and D are locally finite, which is assumed, then the linear product exists and is locally finite abelian. Aha. So it's I can take back this. We don't need abelian. We only require k-linear. And it's a universal property, so it's unique up to unique equivalence of categories, of linear categories. Consider the case that C is equivalent to the category C, comma, where C is a co-algebra. The K co-algebra, and these are co-modules over the co-algebra. I think you know what that is. Just dual to definition of module, which we have, which I have given. Is clear to everyone, or should I? It's not clear. I will define. Let me put it like that. I will define co-algebra and co-module in a monoidal category later on. So in case you are not sure about it now, I don't want to repeat it now.
You did.
I did. Okay, thank you. I don't remember. But the D co-mod. So for C and D, some co-algebras, and then it follows that the linear product is again equivalent to co-modules over a co-algebra, namely over one, which I get as the tensor product of C and D. And again, that this vector space has a natural structure of co-algebra. This is easy to see. I don't want to show it here. And we require in the definition that this function is right exact, but it turns out it's actually exact. And if you look at the morphisms in the linear product of two objects, x box times y and x prime box times y prime, notice that not every object in the linear product is of this form, but these are special objects. Sometimes they are called box times factorizable. This is simply isomorphic to the tensor product of the individual vector spaces in C and D. So this is the object in the linear product which corresponds to the pair x and y in the Cartesian product. And isomorphic here as a K vector space. Then finally, if f from the Cartesian product of C and D to some E is any linear function, that is exact in both variables. Then this defines uniquely an exact functor from the linear product to E. And in particular, if I have two right exact functors between pairs of categories, finite categories, so if I have S, say from C to C prime, and G from D to D prime, both of them right exact. And all of the categories locally finite is enough. Then there is a functor f box times G from the linear product of C and D to the linear product of C prime and D prime, which is obtained from the Cartesian product of functors between the Cartesian products by an extension which is canonical due to the universal problem. And then a lemma. If I look at the linear product with vector spaces, then nothing happens. So this is a unit for the linear product. So to be precise, if I take the linear product with any category, with any finite category C, this is equivalent to C and also in the other direction. Now, in this part of the lemma, you could ask, why do we talk about co-algebras and co-modules and not algebras and modules, which we might like more? It turns out, in full generality, that the theory of co-algebras, if you allow for infinite dimensional vector spaces, is in a certain sense simpler than the theory of algebras and modules. And as a consequence, in this case here, we do not have to require finite dimensional for the algebra, even though in the notation I have not made this clear. But if we go to algebra or the co-algebra, we go to algebras and modules, and we have to require finite dimensions. And this is stated in the next lemma. Assume that C is equivalent now to A mod and D equivalent to B mod, where A and B are finite dimensional. algebras. Then it follows that the linear product is equivalent to I should say as I mentioned before, when I talk about modules, then unless otherwise stated, I talk about finite. So here this is important, and then the linear product is equivalent to the category again of finite dimensional modules over the tensor product of the algebras. And once you have the proof here, you just dualize it and get the proof here. But then you could ask, well, why not just have an independent proof here and dualize it? If you do this, and then you have to be careful with the notion of dual vector space, which in the infinite dimensional case, is not completely trivial. So that's precisely the reason why these situations are not in bijection. And then a remark about the requirements we need for the linear product. If we relax the requirements, then we do not necessarily have a linear product. So the linear product does not exist in generality for arbitrary abelian categories. But there are variants which exist for other classes of categories, more general classes. And I do not want to go into details here, but just mention some names, and you will find them then in the list of references. There's a paper by Franco. There's a paper by a person I don't remember at the moment, and Johnson Fried. And there is a paper by Wendy Lowen and two collaborators. Next point is we have this definition of finite category meaning equivalent to a category of modules, finite dimensional modules for finite dimensional algebra. But in general, there's no reason why this algebra should be uniquely determined. There can be different algebras which have equivalent representation categories. For example, that happens even for group algebras. So, and there is a classical result about how different algebras which are related in this way are related, and this is called the classical Morita theorem. It says that let A and B be associative unital. I don't say this always. Algebras over a field K. No, sorry, it's more general. Over a commutative ring R. you could take a field for simplicity. Then the following are equivalent. One, the categories of, by this I mean the category of right modules acting from the right. Category of right A modules is equivalent to the category of right B modules. The category of left modules are equivalent. And there are bimodules. Let's call them M, which is an AB bimodule, and N, which is a BA bimodule, such that the functors tensoring anything over A with M. So that I should write. Let me first continue and tensoring over B. Let me see, with N. Give an equivalence between the category of B left modules and A left modules, and analogously for right modules. And actually, this is not just an equivalence, this is what is called an adjoint equivalence, but I haven't defined adjoint yet. Again, I have to apologize for using something. So what do you do here? You take, let me see, do I write this correctly? Yeah, if I, no, this must be right modules. Let me see. In order that I can take the tensor product over A, I need a right module here, and then a tensor, I forget the A action, I get again a right module, so this should be actually mod B and mod A if I formulate it in this way. And here I take a right B module, so this is in the opposite direction. And terminology, which I don't write down, is that if you have two algebras which satisfy these equivalent properties, then we call them Morita equivalent. And if there is a we talk about the property of algebras which is invariant under Morita equivalence, then we say it's a Morita invariant property. So I will give you some examples. First, a remark. In particular, it follows that if A and B are Morita equivalent, then there are isomorphisms. But then there exist such bimodules. So we can take the tensor product with n. From the left over, so here I have taken tensor product from the right. If I would have taken tensor product from the left, it would have been product modules. So I use this formulation now. Well, there is A is naturally an AA bimodule, where the action goes from the left and the right. It's just a multiplication. I don't write this down. And then if I take the only possible double tensor product over A with these bimodules, then I get the algebra B as a bimodule over itself. Maybe I write for AA. It doesn't look nice. N is in particular left B module and M is the right B module. So this vector space here inherits naturally a structure of EB bimodule, and the statement is isomorphic to what is called a regular bimodule B. So B as a bimodule over itself, and conversely, if I do it the other way around, I have an analogous isomorphism of bimodules. And also another terminology which we will not need, at least not for now, is that these isomorphisms here are actually structure. So you can talk about Morita context consisting of these two bimodules and specific morphisms here. And then there are statements about Morita context. And in particular, these isomorphisms are not completely arbitrary. They will automatically, in order for these being isomorphisms of bimodules, satisfy certain mixed associativity conditions. But I will not talk about it. So now about Morita invariant properties. Being simple or semi-simple, then in case you have encountered these notions being left or right Artinian, being left or right Noetherian. And there is another important example, which, however, at the moment I do not include because I have not defined it. Namely, being or admitting the structure of a commutative Frobenius of a symmetric Frobenius algebra is an example for Morita invariant property. Whereas admitting the structure of a Frobenius algebra, not necessarily symmetric, is not Morita invariant. And then to explain why I introduced this. one can show. Well, it's more or less a triviality from once we have the Morita theorem. If C is a finite category, then the algebra A such that C is equivalent to A mod, finite dimensional A modules, is determined uniquely after Morita equivalence. Maybe I should call it corollary. There's not really nothing to. And another interesting statement about finite categories, in the sense defined here, is the following. If C is a finite category and H is a functor from C op to vector spaces, the following holds. H is representable. And I mentioned the notion already. I don't think I have formally defined it. So maybe I do this here. So this means that I can write H apply to any object where there exists an object Y in C such that H of something is the same as the home functor. Well, H is a home functor with this object. The statement here is that H is left exact. Remember, I have stated that the home functor is left exact. And now it turns out precisely all the left exact functors are home functors in 0%. So we are finished with this section. And now we come to a somewhat longer section. So we will not finish that today, which is called semi-simple categories. And there are some areas in physics where people not necessarily like to talk about categories, but implicitly they do. But an explanation of why they don't do this explicitly is that all the categories they are considered semi-simple. And they have many special properties, and those properties are just assumed in an appropriate version in corresponding applications. But for us, this will be just a special class, and maybe at some point I will try to motivate why one should also look at non-symmetrical categories. So we need a bunch of definitions. Remember, I defined linearly simple object. Now I define simple object for the case of an abelian category. For the moment, one can actually define it in somewhat more generality. So this is an object in C that has precisely two subobjects. Well, if you remember the definition of subobject, it's clear that every object is a subobject of itself. And if you remember the definition of abelian, you should know that every object has a zero object as a subobject, and simple says that there's nothing else. And generally, a semi-simple object in the abelian category is an object that is a finite direct sum of simple objects. Remember, we defined a direct sum at the beginning of today's lecture, and we require a finite direct sum. In definitions you find in literature, finite is not always assumed, but actually it's sometimes assumed without stating it. So you have to be a bit careful with definitions. And then we have the notion of a semi-simple category. This is a category where every object is semi-simple. An abelian category C such that every X in C is semi-simple. And there's a notion of finitely semi-simple category. And this finite is not the same as finite here. This is a semi-simple category with a finite number of isomorphism classes of simple objects. Finitely many simple objects up to isomorphism. Side remark, which I don't write down, the zero object is not simple. It has precisely one object, namely itself, which is zero. And so some people say it's too simple to be simple. Actually, that's nice that it follows directly from the definitions. It avoids having to exclude a zero object explicitly in certain other definitions. Like when you define not like when you define, for example, a semi-simple Lie algebra, where you have to say where depending on how you formulate it, say explicitly that it should not be. Examples? Category of vector spaces of finite dimension. And, often I assume this without writing it, but now I write it explicitly. This is finitely semi-simple. For any field K. So here I could also allow for algebra, not algebraically closed. Then the category rep G, no, rep K of G, so the K-linear representations of G. Where G is a finite group. Is semi-simple if and only if the characteristic of the field does not divide the order of the group. Then examples which I might use much later in the course is the category of representations of what is called a rational vertex operator algebra. It's finitely semi-simple. Here that is actually also finitely semi-simple. I didn't write this level. And then also what is called a fusion category. Is finitely semi-simple. I think I have to stop here. Maybe I can announce with a side remark, which I then will start on Thursday. Namely, usually one defines the notion of simple objects for abelian categories, and then this is the usual definition, but one can actually define simple also in a somewhat larger class of categories, and then sub-object is not the right concept, but one has to work with quotient objects instead. Okay, thank you for today.